In this lesson, we'll focus on how we can begin working with flip fluids in Houdini. So I'm just going to start with a totally clean scene here in Houdini. And I'm going to lay down a box. I'm just going to control-click the box icon on the shelf here. I'm going to come over to this shelf on the right. This is the particle fluids shelf. Now, not the particles shelf. That's something completely different. But the particle fluids shelf here, which is the first, second, third, fourth, fifth one over. Now that we've got our box selected here in the viewport, we'll go ahead and create a flip fluid from object. Now, hang on, this is a flip fluid from object, and we're on the particle fluids tab. So is a particle fluid a flip fluid? Are they one and the same? Or what's the difference, if there is a difference? Let's take the next 2 or 3 minutes and actually just kind of discuss exactly what a flip fluid is before we actually start making one. So I've generated a few slides, if you will, just a little quick 2-minute presentation here so we can better understand exactly what a flip fluid is. So FLIP, F-L-I-P, is just an acronym. And it's an acronym that stands for a big fancy scientific word, fluid implicit particle. Now, it's not really important that you understand what a fluid implicit particle is or exactly how it works or any of the algorithms that make it work the way that it does. What is important is that you understand that it's a hybrid of 2 different tool sets. See, in the old days of Houdini, we were given 2 ways to create fluids. One was using a volume grid. Now, volume grids were made up of these little boxes. Now, because they were volume boxes, sometimes you'll hear the term voxel or volume box used to describe these little volumes, but just know that what they are is the one and the same, the terms mean the same thing, volume and voxel. So information about your fluid would exist within one of these little boxes. Now these little boxes were stacked in all 3 dimensions, and it created something similar to what you would think of as a 3-dimensional Excel spreadsheet. So each one of these little volumes held information about the overall fluid. Where the fluid was moving, how fast it was going, if it had pressure, what its surface looked like, if it was on the surface. And this was produced very, very good results for a long, long time. Now, there were some problems. If your fluid accidentally needed to go somewhere that was outside the bounds of the box, it simply couldn't. It would just disappear. If your fluid, for any reason, did not have enough boxes or volumes in the grid, certain points of it might just disappear completely. It required a lot of resolution. It also required that even if you knew your fluid simulation would be this big in your scene at the end, if it started off as simply a drop in the corner of the scene, every single box would have to be predefined and calculated. So it was very inefficient. So you may only have a little bit of fluid happening here for the majority of the scene, and then at the end it's supposed to shoot around in the scene. Well, every moment that that fluid exists, even when it's just in this tiny little corner here, it's being calculated throughout the entire grid. So very inefficient. But again, predictable results and results that looked good. So on the other hand, we were also given a tool set that used particles. Now, particles basically took the exact same idea, only instead of using a grid to calculate on, like a little Excel spreadsheet, it just used these little points. And these little points could communicate with each other, but they were not limited to a grid. They could exist anywhere in the scene at any moment without having to be predefined or calculated. So they were very fast to calculate, and they could go anywhere. They weren't limited by the box, but they were also very unpredictable. A lot of times, particle fluid simulations like this would explode, behave erratically for no apparent reason. They also required an extra step prior to rendering, which was you had to generate a surface, whereas using the volume-based system, the volume grid system, there was a surface that was already created for you as a part of the calculation. So, efficient to calculate, but required an extra step, and were highly volatile. They would explode often. Or a set that was sort of slow and clunky and inefficient, but stable and gave good results. That's what we used to have to work with. Flip is actually a hybrid system of the two previous volume-based and particle-based fluid systems. Flip basically just calculates the particles' movements on the grid. However, the grid, volume grid here, is defined by where the particles exist in space. So they basically talk back and forth to each other. So one is dependent on the other. That's basically what a flip simulation is, which is why it can be under the particle fluids shelf inside the interface. It makes sense because we are working with particles to build a fluid. But as you'll see here in just a second, when we generate our first flip fluid, we're also working with the volume tools. So we have two complete tool sets at our disposal when we're working with flip. Now, you'll learn more of this as we go through the interface, and in future lessons you'll see more and more of these terms and you'll become more familiar with them. But for right now, just take away from it that the term flip is a term that refers to fluids. It refers to a hybrid fluid set that uses both volumes and particles. In the next lesson, we'll actually generate a flip fluid.